For part two, we're once again going to start with an example. And this is you can think of it as the good twin of the evil twin that we talked about in part one. And then I'm going to use that as a motivation to talk about a topic that I've been working on a lot over the past couple of years, which is building data platforms to build health algorithms and essentially to allow other people to build health algorithms, because I think the data is a real bottleneck that's holding this whole field of applying computation to health back. But as a motivating example, let me tell you first about this algorithm. And this is work that was led by Emma Pearson, who's on faculty at Cornell Tech now, who's wonderful. She did this work when she was a PhD student at Stanford, and she is just fantastic. To tell you about this algorithm, I first need to tell you a couple of facts about pain. So pain is, I think as we've seen from the opiate story in the US over the past few years, an enormous problem in society, but it's also a problem that, like most, is unequally distributed. So it's very concentrated in particular groups of people to, I think, a surprising extent, at least for me, before I started to think about this. So if you look at there are these surveys that just ask people, like, have you been in severe pain over the past day or two? And the rate at which Black patients answer yes is twice as high as white patients. So you just think about the, yet another kind of aspect of unfairness in society. Just imagine being in severe pain and how much more likely you are to be in severe pain if you are Black, if you are poor, if you're less educated. So all of these things have these tremendous gradients in society. And I think, I almost, whenever you see another instance of a disparity, it's very tempting to be like, well, yeah, everything is kind of more concentrated. And specifically, things that cause pain are probably more concentrated in these groups. And so we're going to be using as our model organism for this portion of the talk, knee pain, and specifically the most common cause of knee pain, which is arthritis in the knee. And so if you look at, for example, knee pain and try to explain it with knee arthritis, you can make some progress. So there are these gradients of the prevalence of osteoarthritis of the knee by income, by education, by race. But interestingly, that is not the whole story, because there are these really nice studies that actually adjust for that and still have this surprising finding. So the way these studies work is basically, okay, for knee arthritis, we're going to take people who have knee pain and whose x-rays look the same. So we're going to condition on the degree of arthritis in the knee, and then we're going to compare pain scores now that we've kind of zeroed that out. And what those studies find is that these groups still have more pain. So even when I condition on the degree, the severity of arthritis in the knee, Black patients, for example, still report much more pain than white patients from knees that look the same. So how does the literature kind of square this? Well, I think the basic idea, to caricature it only a little bit, is to say, well, if the source of the pain is not in their knees, maybe it's somewhere else, and maybe it's in their heads. And this is actually, I think, not a pejorative statement about this research at all. There's a bunch of very good research that shows, for example, that if you apply the same physical stimulus to someone in the lab, and one person is under more stress or has a history of anxiety, they actually report higher pain scores from the same stimulus. There's a lot of evidence that anxiety and depression can manifest as pain. There's also some evidence from psychology around just kind of bandwidth for coping, when you have a lot of other difficult things going on in your life, that can also lead to... So there are all of these mechanisms by which things that are not in the knee can translate into higher pain scores in the knee. And then there's also just these same disparities that we talked about in the last hour in the medical system. So two people with the same knee problem can have different access to therapies that can help with that knee pain or not. So, all of these explanations are very plausible and I think very grounded in evidence, and all of them have in common that it's not in the knee, it's somewhere else. So let me just walk through, a concrete clinical scenario, just so you kind of like see how this enters into the clinical practice world. Imagine you're a primary care doctor, and a patient walks into your office with knee pain. You might send that patient for an X-ray, and that X-ray might come back looking normal. So the radiologist might say with the X-ray, like, you know, no signs of osteoarthritis, or like mild osteoarthritis. And if you take that literature seriously, what that would imply is that if that patient is Black, it is more likely for that patient who is in pain to come back with an X-ray that says, where the radiologist says, like, well, there's nothing here. And that's going to lead you to start looking elsewhere. So rather than referring that patient to an orthopedic surgeon for consideration of a knee replacement, to a physical therapist or whatever, you might like ask some other questions about anxiety or stress, or you just might consider going down a very different path from one that you would have gone down had that X-ray came back with like a bunch of stuff in the knee. Everything I've said so far depends very heavily on one thing, which we've left implicit, but now I want to make explicit, which is disease severity, like the degree of arthritis in the knee. So that's the central concept in this whole story, is like we've zeroed out this object. But what is this object? How do we measure it? Well, I'm going to show you the current state of the art in measuring knee arthritis. It's this. So a radiologist looks at a knee X-ray and then grades it according to a grading scale based on the detailed appearance of lots of different parts of the knee. So the radiologist is just going through a checklist and going through all those different compartments of the knee and looking at the irregularities present and the surface of those things. And the most common such grading system is called the Kellgren-Lawrence grade. And it was developed by these two doctors, Drs. Kellgren and Lawrence, published in 1957. And there's one curious thing about these studies when you go back and look at them. So they were studies of coal miners in Lancashire in England in the 40s and 50s, and they were sometimes comparing those coal miners to office workers and just getting knee X-rays and stuff like that. And when you go back to those studies, there is no mention of the subject's sex or race, because it was all the same. So, so that's kind of an interesting clue that there might be something going on here that we're missing. So, you know, and because this is a talk about algorithms and bias, you might wonder if, like, okay, is this where we're going? So if humans are overlooking causes of pain that might be affecting Black patients that are in the knee, but that we're just like not seeing, we're not including in our current scoring system, we might like an algorithm to help. But there's one problem, which is that if you look at the way the machine learning playbook kind of works in medicine, it basically works like this. Like, all of these papers are about the knee, but you can kind of like just look at all of the big papers that are doing, you know, machine vision applied to medicine are basically saying, okay, let's get a bunch of X-rays, electrocardiograms, whatever, and then let's train an algorithm to read these X-rays. But what are we training the algorithm on? We're training the algorithm on the radiologist's interpretation of that X-ray. And so all these papers, that's what they're doing. Input image, output a prediction on what a human radiologist would say about that image. And this is very much like the ImageNet playbook. Like, what is the ImageNet playbook? Well, it's just like get humans to caption the image and then just predict that from the pixels. But notice that matching human performance is exactly what we don't want to do if we're worried that humans are missing something in that image. So there's kind of like this basic problem with applying that playbook out of the box here. So what we did in this paper was very simple, which is to try to find a better, or at least a different target for prediction. And in particular, if you want to characterize the standard playbook as learning from the radiologist, in the sense that it's inputting this X-ray and then outputting the Kellgren-Lawrence grade that a radiologist would assign to it, well, it turns out that there's another human whose opinion you might be interested in about this knee, and that's the patient. And so that's what we're going to do. We're going to train the algorithm to predict not what the radiologist would say about this knee, but what the patient would say about this knee in terms of the pain score that the patient is asked to give about the knee from 1 to 10. So it was not easy to find these data. It's comparatively easy to find data that can be used to run the standard playbook, in the sense that you can get the X-ray and the interpretation of that X-ray, because those two things live together on the same computer system in the hospital electronic health record. So it's actually kind of easy to get the images, to get the text of the note, and to kind of like put those together. But it's a lot harder to find data that match those X-rays to the patient's experience of pain. And I think this is, maybe a broader comment about the medical system. I think the medical system cares a lot more about what doctors think than what patients think. So I'll tell you how we got these data. So there's this NIH study called the Osteoarthritis Initiative. And one of my colleagues had done some analyses with the pain scores and disability. And so, you could get the kind of structured data. But the images, the NIH was like, yeah, eventually we're going to make the images public, but they were not public. And so I spent a while emailing with the NIH people, and they were like, yeah, well, there's security, and we have to build our computer interface, and because it's NIH, it's just everything takes a million years. But the person at NIH was like, oh, but one of your colleagues at the Brigham, so I was I was on staff at this hospital in Boston, one of your colleagues is actually a co-investigator on the study, and he could actually give you these images if you had an IRB. I was like, great. The only problem was I was moving to Berkeley in 2 weeks. And so I immediately went to buy a big hard drive, and I emailed this guy, and I was like, will you please give me these things? I'll write the IRB. And he's like, sure, but the images they're going to take about a week to transfer over because they're pretty big. And I was like, okay, I'm going to come by your office today. So anyway, so I got them, and I brought the hard drive to Berkeley, and then I gave it to Emma. And then she wrote this paper, which was fantastic. And once you have those data, it's a very straightforward problem. So basically, input the images, train a standard neural network, and output a prediction on the pain that the patient is reporting. So same playbook, swap out the label, which is a recurring theme. I want to make one point about predictability, which is that, think about what we're doing. We're inputting the pixels, we're outputting the pain score. If the pain is predictable from the pixels in the X-ray, there is signal for pain in the knee. Now, there is some confounding. We'll get into that in a second. But basically, sorry, ignore this. This was from the framework. If you think about the pain as so a lot of people, have this suspicion about pain scores. So pain is so variable. You ask someone how much pain they're in, and they woke up on the wrong side of the bed, they're just going to say more, or if they're in a good mood, they're going to say less. So there's all these things that it's high variance, it's noisy. But if the algorithm can predict pain from the image, it's not noise. There's something in that image that is correlated to the pain. So I think that's kind of an important point. Okay, so now we've got the pain score, we've got race, we've got the doctor's grading of the knee, and then we've got the algorithmic grading of the knee based on the pain prediction. And so let me show you a couple of facts about those things. So this is an NIH study that enrolled a very diverse sample all across the US of people who had knee pain and knee arthritis. And if you just look at the unconditional difference between black and white patients in that sample, this is a very weird scale. No pain on the scale is 100. Severe pain is less than or equal to 86. I don't know why it's this way, but that's the scale. The difference between black and white is about 11 points, so it's more than halfway between no pain and severe pain, on average, between black and white. It's a huge difference in pain. If you adjust for the radiologist's severity measure, you can explain 9% of that gap. So 9% of that gap correlates to the degree of arthritis in someone's knee. If you condition on the algorithm severity measure, you account for about half of that gap, so many, many times more than the radiologist's judgment. So what the algorithm is finding in that image is doing a good job of explaining pain disproportionately, the pain that is affecting Black patients, that is unexplained by these other, by this other score. And we get similar, although less pronounced, results for income and educational differences. So there's one problem to address here. Well, there are many problems to address, but the main one that you probably are wondering about is like, well, an algorithm could probably do a good job at this task if it were just recognizing that some patients were Black and some were white from the X-ray. So it doesn't need to predict pain at all. It can just predict race, and it knows that Black patients have more pain. So if the algorithm can just guess who is Black, it's going to do a good job of guessing who's in pain in a way that could be completely unrelated to anything mechanical about the knee. And you can imagine similar things happening with body mass index or lots of other things. Now, the good news is that we measure all of those things. So the story here would be, well, the algorithm is reconstructing this variable from the pixels. But we have that variable, like not a reconstructed version. We actually have the variable. So we can just control for that and see if the algorithm's ability to predict pain is affected by controlling for the real version of that variable rather than the reconstructed version. And the interesting thing is that it has basically no impact on the abilities, on the algorithm's ability to predict pain from the image. So if you control for race, for body mass index, for lots and lots of other things that we have and observe in the data set, you're not detracting from the algorithm's ability to predict pain. Yeah.
Is it true that, in your data set of X-rays, the people who would get X-rays to begin with already have some issues?
Oh, great. Yeah, so great question. So is there some bias in who's getting the X-ray? In a normal healthcare setting, yes, absolutely, and it could be a problem. This is a longitudinal study where everyone who's enrolled gets the X-ray. So there's probably some bias in who is enrolled in the study, but they did do kind of the study was very specifically trying to get a very diverse population, so they had huge outreach to non-white populations to poorer populations and things like that. So I think a lot of those selection concerns are less worrying in this setting. Other thoughts or questions? Okay. So the other thing that you often see popping up in some of these studies is like, well, this longitudinal cohort was enrolled at like 6 or 7 different sites across the country. And you could easily imagine that there are differences in pain across those sites and differences in medical equipment across those sites. So in a lot of these medical papers, like one thing you find is that the algorithm is great at predicting something, but it's because the X-rays from the ICU look different from the X-rays in the ER. And if the algorithm can figure out which ones are in the ICU, it's going to be a great predictor of mortality because they're in the ICU. So we can basically check for those kinds of things by cross-validating across the sites of the study and making sure that when we predict pain in 6 sites and see how it does on the 7th site, it still does well, and run that for a bunch of these different strata of the study. And it doesn't look like it's picking up on any of those things. And then the last thing, which is kind of interesting, is that you could imagine a less impressive version of this, still interesting, but a little less interesting, is to say, well, the algorithm is just rearranging things that the radiologist already knew. So the radiologist is giving us this vector of lots of different subscores about the knee. And so, maybe we're not adding those up or weighting them properly, and maybe the algorithm is just doing a better job of weighting the things that the radiologist is already seeing. So one way to think about that is to say, well, how much of the algorithm score can be explained with the things that the radiologist is annotating about the image? And it turns out only about 2/3 of the algorithm score is that. So 1/3 of what the algorithm is seeing is genuinely new signal that radiologists are not currently annotating or capturing. So this is important. We found it interesting, but it's also important in the sense that, to go back to that clinical scenario we talked about, how do doctors use this score, this osteoarthritis score? They use it in a very real way to figure out who needs things like a knee replacement. So I don't know if you've had friends or relatives who've had knee replacements, but pain can be crippling, and knee replacements can be life-changing. It can be the difference between not being able to leave your house, do errands, like get up and down from the toilet, like really just like it's a very different life when you can't use your knee. And these things can be really transformative for patients. But we don't replace the knees of people just because their knees hurt. There has to be a knee problem. That's why you need a new knee, is because the old one isn't working. So if it looks like there's nothing wrong with the knee, you're not going to get a knee replacement. And this isn't just like clinical guidelines, this is insurance guidelines. So your insurance company will not pay for you to get a new knee unless you are above a threshold of osteoarthritis severity. So these are like real, the score is very, very consequential for patients. So if you want surgery, you have to have two things, severe pain and severe arthritis. But who decides what's severe? So what we did is we took all the patients in our study with severe pain. And then we figured out, okay, well, of those patients, which of them has severe arthritis according to the human radiologist? Call that N. Now let's swap in, instead of the N patients who have the worst disease according to the radiologist, let's swap in the N patients who have severe disease according to the algorithm. And let's just see what that does to our population. It would actually double the fraction of Black patients' knees that are eligible for surgery. So these are big differences, and they could actually go a long way to explaining a fact from another literature, which is that there's a huge disparity in access to knee replacement surgeries. So if we assume that Black patients have arthritis that is, at least as bad as white patients, like the rates of knee replacement are, many-fold lower for Black patients relative to white patients. And this could be part of the story, is like we're just not seeing the extent of disease in Black patients because we're looking for things that are fit to this older population of coal miners in England from 70 years ago.
I don't know if you talked about this already, but what are some factors for which radiologists would be diagnosing like these knee conditions differently just based on these X-rays, or is it like an external, like they have like a chart thing?
Yeah, great question. So one of the really nice things about radiology is that it's not that there are no unobservable factors, but radiologists' job is, to a first approximation, sitting in a dark room, looking at images and generating text. So, and because of the way the medical system is structured, they need to do that quicker and quicker and quicker to kind of like keep their reimbursement and volume numbers and things like that. And so they have the option to look at charts, but they rarely do. So they're really just looking at the image and commenting on the image. And sometimes they look at a prior image for comparison. So that's kind of like one thing that we didn't address here and that most people don't address. But to a first approximation, it's not bad to assume that radiologists and algorithms have access to the same material, just because of the way radiology works in a real setting.
So is it true that like somehow in the medical training setting, they are not given enough different, like from different races, means from different races?
Yeah, I mean, I'd say that the problem is even deeper than like the medical training. It's how medical knowledge is produced. So like, what are they trained on? Well, they're trained on the outcome of these studies that are done in very specific populations at specific times. That's what we learn in med school. So what is arthritis? Well, it's these like criteria that you just memorize and then look for in the X-ray. So even if you were exposed to a bunch of different patients, like these radiologists are exposed to lots of non-white patients. They're just not seeing the things that are causing pain in those patients because they're not trained to look at them. And if you think about like how, in many ways, I find it kind of miraculous that we know anything about medicine at all. It's really like kind of a testament to how the human mind works in like going from a very small set of X-rays in these coal miners to understanding like what arthritis is. It's like a super complex pattern matching exercise that like at those sample sizes, algorithms could never do. So humans have built up medicine in this kind of miraculous way that's really cool, but it's also no surprise that we miss stuff and get some stuff wrong. So I think that's really one of the things I'm most excited about for machine learning in medicine is this medical discovery angle, because I think so many problems are very well suited to these approaches. Yeah, so I wouldn't, does it help to not think of it as a training problem, but as like a production of scientific knowledge problem? Yeah.
So there's variability in the decrease of pain after a knee surgery, right? Is this kind of model able to predict that individualized treatment effect?
Yeah, I mean, so I think you would have to buy an assumption that if the problem is in the knee, giving you a new knee will solve the problem. So I think that's the core assumption here. So you're right to ask about it. It's the assumption that underlies all of our current practice. But could this be a different kind of pain? You know, you could imagine a story where it's like, oh, what we're seeing in the knee X-ray, like what's different is that it's a tendon problem, or like you're seeing part of a muscle, but really the pain is coming from all the way up here in the groin, and you can replace the knee, but it's not going to solve this problem. So very good question that I don't have an answer to, and we're far from being able to say anything about treatment effects. What we're saying is that a lot of the pain that has been attributed to somewhere outside the knee is visible in the knee. There's a corollary here, which is kind of obvious, but still interesting, which is that when you look at the knees that are in severe pain, but ineligible for surgery, under the traditional score in blue or the algorithm score in red, there's far fewer of those, like residual unaddressed pain in Black patients. And this is important because these are the people who, you know, severe pain but not eligible for surgery, they get prescribed a lot of opiates because, you know, it's like someone has pain, they come in, you're like, I don't know what I can do for you, it doesn't look like it's your knee, your problem is pain, how do you treat pain? Okay, so I'm going to switch gears and talk a little bit about, yeah.
So now that we know that there is something in the image, so we can use an algorithm, or we could think about retraining doctors. So is there any thinking along those lines? Is there anything being done?
Yeah, so a couple of things that we're interested in but haven't done. I should point out that that data set, it's called the OAI data set. It's, if you look at that paper, it's a Nature Medicine paper. Emma Pearson is the first author. There's a link to she has the Git repo is up, and you can link to the NIH data set and download it. So all these things are like doable things if you're looking for some interesting data to play around with. One of the things we were thinking about doing was something like, okay, let's take two knees that are matched on the radiologist score, but are discordant in algorithm score, just asking the doctor to kind of in a very free-form way comment on like what's different about these knees. So that was like one way to, you know, the way we've been thinking about it is like, how can we get the knowledge out of the algorithm and back into a human head? You can use some of these interpretability kind of techniques, but in their current form, they kind of tell you like where, like which pixels correlate to the, you know, more or less pain score, but it's not, yeah. Yeah. So there's kind of like, so that said, I think there's a ton of interesting stuff to do in terms of interpretability there. The other thing is that 20% of the patients in the study have an MRI of their knee, which gives you a ton of additional resolution as far as like what's there. So mapping from the pixels that seem to correlate with better or worse predictions to the parts of the MRI would also be super interesting. So I think there's this paper I have a kind of love-hate relationship with because I like the paper a lot, but it raises a lot more questions than it answers, and it would be nice if other people could answer those questions. So yeah, but super interesting and important. Any other thoughts on that, the knee stuff, before I'm going to switch gears a little bit? Yeah.
Yeah. Isn't the upshot, I think, a little bit that it is actually the knee, and that maybe it's not only race, like not only black people will benefit from this like a better understanding of what's causing knee pain, and then that could be the way to be the narrative for why we should also shift. Like this isn't a quote-unquote social justice problem. We're actually doing better medicine by understanding it better.
Yeah, I fundamentally believe that statement. I think, you know, one statistic from the paper is that if you just look at the R-squared for explaining pain in everyone, it's just better than the radiologist's judgment. So I think for me, in addition to the equity considerations, there's just a basic scientific process point, which is like if we're interested in understanding where pain comes from, this is a really powerful tool that benefits everyone. So yeah, I completely agree with that. And I think that's very related to what I wanted to talk about next, which is there's this funny thing about practicing medicine, which is that, you know, from the outside, like people are wearing lab coats and there's all these like machines and it looks very science-y, doesn't it? It's kind of like, you know, people generally appear to know what they're doing. Doctors certainly speak very authoritatively. But the reality of being a doctor is like, you have no idea what the hell is going on the vast majority of the time. So, and it's not just, I don't think I'm like a great doctor, but I'm like not a terrible doctor. People come into the ER, like 75% of the time you're like, I don't know. It's not a heart attack. It's not a stroke. It's not pneumonia. And they're like, well, what do I have? And you're like, I don't know. It'll get better. Or not. But, you know, can you leave now, please? Because I got other patients that I have to deliver this unsatisfying message to. So there are just these deep mysteries about medicine that I think it's easy to forget this when you look at the bureaucratic, technical edifice of the medical system. It looks like we kind of have our shit together, but we really do not. And I think that's because these problems are really hard. So like, you know, there are all of these problems that are not just unsolved mysteries in medicine, but that are also great machine learning problems. So pain, like the vast majority of time when a patient comes into the ED, into the emergency department with pain, we have no idea what's causing the pain. We check for like bad things, but then the residual is huge. And we're like, well, it's going to go away or not, or, you know, go see someone else about this, or have some opiates. So like a lot of the attention about the opiate pandemic very appropriately is focused on pharmaceutical companies and like poor behavior from doctors and things like that. But I think that obscures this very fundamental point, which is that the vast majority of pain, we have no idea what causes it or what to do about it. Like, have any of you had back pain? I have back pain. I have no idea why. Like, over 5 years, I've come up with some exercises that maybe have made it better. Like, I don't know. What is that? What do I do? Like, we don't know. But if you think about the playbook, that at least is like, we're pulling up one corner of the rug in the knee pain paper. It's like, okay, we have pixels. We have pain scores. Let's kind of like start doing that as a way to figure out like, well, you know, people with all this unexplained pain, what does it correlate with in the image? Can that help us make progress? Can we go back to the lab and figure out, okay, well, what is that structure? What can we do about it? I don't know if you know this fact. This is a crazy fact. There's this entity called sudden cardiac death, which is exactly what it sounds like. It's like your heart just stops. The epidemiological estimates are like 300 to 400,000 people in the US every year. Their heart just stops. And even ex post, like the risk factors are not clear, let alone ex ante when you could actually do something about it. Great prediction problem. Cancer. We do a lot of biopsies. We do a lot of mastectomies and prostatectomies and colectomies. Most of those people probably would have been fine without it. At the same time, a lot of people get diagnosed, like their first cancer diagnosis is when it's metastatic. A lot of people still die of cancer. Why is that? COVID brought up a ton of really fascinating things, and I think it's no exaggeration to say that like someone gets COVID, someone gets exposed to COVID. We have no idea who is going to develop like the runny nose version of COVID or like the ICU breathing tube, like, you know, death version of COVID. So you can immediately see why all these things are interesting from a machine learning point of view, because a lot of them are mapping from some complex high-dimensional thing like an X-ray or a biopsy specimen or a mammogram or, you know, whatever it is, to an outcome in ways that are scientifically useful. And I think our knee pain paper is like, I like the paper, but it has some problems. It's one very small thing. Science works when, you know, lots of very small things happen. Lots of people are doing things. So where are all the other papers? Like, what are the classic machine learning applied to health papers? So there's one reason for this that I think is more important than any other reason, which is data. So fields just need data. There's no field without data. And, you know, the ImageNet story has been told a million times. There's like lots of other data sets that have, you know, made computer vision possible. Finance, like there's like a lot of rich data on stock performance, financial performance. The Human Genome Project is just a data play. Like the whole thing is just generating data. That's the whole thing. The Webb telescope, I think we've all been like ogling over recently. So it's just like, this is how fields move forward. You need data. And I think as others have noted, the data have to have two qualities. One quality is they have to be open. They cannot be monopolized by one group. Like, you cannot have people denying access to data outside of like their one little insular community. And there's another like more subtle but really important factor, which is like there's some level of curation of the data around important field-defining problems. So like this is, you know, ImageNet, like MNIST, like all these things. Like there's a target that people can aim at and collaborate and compete, and like it's this virtuous cycle where there's a problem to solve. And I think the problem, like the reason that these data don't exist in medicine is just like a classic public goods problem, which is that no one person has any incentive to do this. It would be hugely beneficial to all of us, to people who want to write their papers for their, you know, PhD. But unfortunately, the data are just locked away inside of health systems. And those inside don't really have any incentive to share the data, because when they create the data, they want to publish their own papers, or, you know, the administrators want to find some way to monetize the data, or, you know, there's lots of reasons that they're not incentivized to share. And to compound that problem, the people who are inside, like, are any of you going to go work at a health system? No. Like, and more broadly, like the way everyone is competing for talent in this world of like ML, there's no way health systems are going to win that fight. No one's going to go work at Kaiser instead of Google. It's just like, will never happen. So there's this tremendous mismatch of like the data inside of health systems with all of the people who could do really great things with that data, but cannot actually touch the data. If you're at a university, you might think like, oh, well, I can get my medical school's data. You cannot, because the medical school is a completely separate administrative entity, and you are basically treated like an outside person if you want access to that data. It's really, really hard. There's one exception to this, which is that some data are monopolized by a different actor, which is a tech company. So also not particularly incentivized to share. So the result is this tremendous inefficiency and poor matching, where like, I talk to a lot of PhD students who really want to work in health. And historically, my answer has been like, oh yeah, we can add you onto this project. And then in 2 years, after you've gone through your criminal background check and filled out like 1 million forms and gone to Sacramento to get fingerprinted, maybe we can get you onto this like crappy Windows virtual machine that you could, like, it's just, so it's not good. And that's why everyone goes to work at Facebook instead, because it's just easier. It's also, of course, deeply unfair, because only a privileged few can touch the data, and people without connections are locked out. Yeah.
Will you say something about privacy and its role in all of this?
So I think it comes up all the time. And I think, you know, if you asked the health system why aren't they sharing data? That's what they would say. It's like, oh, well, we have this duty, and there's like, and I think the funny thing is that there are very clear legal frameworks for sharing data. Like HIPAA, everyone like is like, I think sentiment analysis of things related to HIPAA would be very negative, but HIPAA is great. HIPAA outlines exactly what you can do and what you can't do. That's like the federal law that governs like whether a health system can share data and how and when. Like, so the law is very clear on what you can do and what you can't. Nobody's doing the things that you can do. And I think that especially given, you know, like, as you know much better than I, like the many technical solutions to this problem, whether it is like hardware / cloud, whatever, or actual like de-identification in a meaningful way, it's just like, I think it's one of those things that it's clearly important, but I think it's invoked much more to hide the incentive problem than it is a real problem. Or what do you think? Is that like a, you know, the space much better than I do? Like, does that sound reasonable?
I don't know the practical space of you know, privacy in health data. Yeah, I was curious about your perspective. I think it's a real problem.
Yeah,
and I can see
absolutely.
that it would be sort of used as a scapegoat, as to kind of the excuse. So
yeah,
the world I want to imagine is one in which we, you know, can unlock all the miracles of science and knowledge you're talking about, together with you know, privacy protection for people.
Yeah, the privacy protection is absolutely critical. I think that it's not quite a solved problem, but we have a lot of good solutions that I think layered on top of each other would be way more than anyone. Like, it would be way past the reasonable standard. And so given that, it feels like to me, it just feels like more of an incentive problem.
You have anything to add?
Yeah, so I noticed that in your repository, you say everything is de-identified. And of course, as privacy people, we say, ha 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 ha. What does that mean? But, you know, I think these two sets of problems, they just coexist. I tend to agree with you that privacy is being used as an excuse, and it's because somehow or other organizations think there is power and there is money in these data, and we don't want to share them, and we don't want to share that out. I think that's a very, very dominant force. I think the real privacy issues are also there, but I think a whole lot of people would be able to do great work without harming other people through their investigations. And I don't know the path through.
Yeah. So let me tell you about this de-identified, repository of data. And I think this is where the law is useful, in the sense that the law does have a working definition of de-identification, which is not the computer scientist's definition of de-identification, but is nonetheless the law, and so allows us to at least aim at that standard. Nightingale Open Science is the name of a nonprofit that one of your speakers yesterday, Sendal Mulanathan, my co-author, and I co-founded and launched. And the idea is basically like a computing platform that furthers this research and that allows other people to do the research. So we partner with health systems, but also with companies, with government agencies in the US and elsewhere. Step one, to build up their data infrastructure, which is often lacking, especially when it comes to images and kind of other interesting medical data. and then to curate the data sets around interesting and important and unsolved medical problems. We then de-identify to the legal standard those images and the outcomes, and we put them on our cloud where we make them available to you and others for free. And so these data sets have a few different qualities. They are big enough to support, like interesting algorithm development. They're all anchored in some interesting image or waveform. And the reason we like images and waveforms is because they're very rich. I think as that knee pain example shows, there's a lot of signal that humans are not using that is in those images that we can find. They are de-identifiable under the legal standard. And I think most importantly, in some ways, they are standardized across time and place. So an X-ray done here at UCLA looks a lot like an X-ray done not just at UCSF, but also in Taiwan, in lots of other places. And I think that really is an important part of generalizability. And finally, the labels are at least, there's at least one set of labels for all of these data sets that is a ground truth label in the sense that it's a patient outcome, not just a human interpretation. So to give you a flavor, we have a data set we're actually creating now of digital pathology from breast biopsies. So these are people who have been referred to a cancer center for a biopsy, and that block of tissue is cut into slides. And with this health system, they basically have this huge repository of physical slides in the basement of their cancer center that are literally gathering dust. And we bought 2 big slide scanners, and we're just scanning all of them. And I think this is like a really interesting question because, as I think there's a real sense in which we don't quite know what cancer is because we do a lot of procedures on people who would have been fine without those procedures. And we also miss a bunch of people who develop cancer too late for us to save them. So there's some mismatch. And I think that these kinds of data sets have a ton of insights to yield because those images are linked to long-term cancer outcomes, to staging, to the results of other imaging tests, to what happens to the patient later. And ultimately to Social Security data on mortality that lets us find those patients even if they don't get care in that same hospital. So we've done a ton of the work to link these images to a bunch of other stuff that's important and interesting. This is one of 5 data sets that are currently on the platform, ranging from heart attack to cardiac arrest to predicting who's going to get a fracture based on an X-ray to some interesting thing around COVID. So just to give you a sense of what this looks like sorry, I forgot to mention an important thing for this audience is that almost all those data sets have self-reported race, and some of them will also have some socioeconomic indicators too, I think are interesting. So in practice, you basically just go to the website and you, sign the data use agreement. You verify that you're doing nonprofit research, and that you basically know how to not do stupid things with health data, and that's it. And then you get access. And then it's just, Jupyter notebooks, do whatever you want. Free, it's there's a small CPU instance you can use to kind of poke around the data, and then everything else is just compute at cost. And we're working on ways to get your local compute integrated in. One of the restrictions is basically no download. So that was a key part of getting hospital systems to agree to share the data, is that the data have to live on the cloud and they can't be downloaded. So we're working on a kind of way to get local compute in a way that can, take it but not store it out so that you don't have to pay AWS. Whatever. This was launched at NeurIPS last year. Okay. How much time? Okay, 5 minutes left. So the other thing that's missing, which is kind of even weirder if you think about it, besides papers, is products. So I think it's very clear why no one's sharing data for the good of the world and research and things like that. That makes sense. But why hasn't the market solved this problem, at least for AI products? Why is going to your doctor so similar today than it has been for the past 200 years? It's really weird. So part of the reason the market hasn't solved this problem is because there's no, like the market is missing. So if you're a company, let's say you go onto Nightingale, you're like, oh, I've got this really cool idea. I think this could be a company, and I want to turn this into a product that actually scales and that goes into hospitals and stuff. How would you do that? Well, option one is you would partner with, an academic medical center, and you'd write a contract, and you'd get data from Stanford or UCSF probably, or the Brigham or Mass General in Boston, and you would, at the end of a very long and painful contracting process, you would have access to a very small and unrepresentative sample of patients from Cambridge and Palo Alto that is not going to generalize anywhere else in the world because those places are just weird. And so that's kind of one model. And the other model is like for Google to just buy all the data from a health system. But again, it's like, that's not a market. That's like a monopoly. And monopolies are typically not how innovation happens in markets, especially because I think at most of these companies, it's not like their core business is not changing medical practice or research. So this is a different version of the same data problem. And so one of the solutions, I think, is to try to make this market work better. So this is a company that I co-founded and hold equity for disclosure, obviously, that is essentially a platform for product development. And basically what we do is we contract with 5 big health systems, and we get access to all of their data, and we put it in one place. We structure it, we put it in one place, and then you can actually contract with one entity and get the data in one computing environment, but have the equivalent of signing 5 huge enterprise contracts with hospitals around the country. And I think, why do the hospitals do that? Well, because we share some of the profits back to them. But the other thing that I think is worth mentioning is that in a lot of these conversations with hospitals, both for optics, but because of their core business, they're like, look, if we're using patient data in this way, I have to be able to sell this as this benefits patients. And so one of the constraints is that we're not approving anything that does stupid billing optimization stuff. That is not the platform for this. This is for patient care and for patient benefit. And I think that's how at least we're grappling with some of the complex ethical issues around using patient data in this way. Yeah.
Are you a B Corp?
No.
What about data from outside the US?
I'm sorry?
What about data from outside the US?
Yeah, super interesting. I think part of the longer term plan, for sure. Interestingly, most entities that have built algorithms on data outside the US also need data from inside the US to get FDA approval. And so a lot of the interest in some of this stuff has been from people who have a ton of data outside the US, but can't really use that to convince anyone inside the US to pay for it.
And a follow-up to that, is there also a regulatory action you're trying to work in order to have them consolidate?
Yeah, another great question. So I think, let me show you one fact about the data. So unlike most other data that you can access, this is from a very broad cross-section of the US. And so one of the things that we're going to try to do is essentially be a regulatory kind of test, so that, if you want approval for your product, you have to show that it works across lots of different populations of different races and urban, rural, and socioeconomics and things like that. And so we're in a position to actually provide that kind of feedback about the performance of algorithms. And I think that's a way in which it'll hopefully improve the quality of algorithms that are developed and evaluated. So these are the two of the health systems that are already signed on. One is they're all a minimum scale, and they're all chosen because they have some market concentration where we get longitudinal data, and where we get just a lot of different kinds of populations. So one is a Midwestern rural healthcare system in the Dakotas. One is an urban health system in San Diego. Both huge and lots of interesting things to do with it. So let me just wrap up and say that, I think the reason I'm excited about the work that I'm doing is because algorithms, I think, can do a lot better than we can. And we have a few papers on this that I didn't mention, but I'm pretty confident that there's huge gains from incorporating algorithmic predictions into medical practice and medical planning and scientific research. And that we need to keep that as our North Star, not just reproducing all of the errors that doctors make and all of the biases that are built into our system. And I think to achieve that goal, I hope I've convinced you that we need to pay very close attention to aiming algorithms at the right target, that have the right value system, that the algorithms are learning from the good parts of us rather than the bad parts of us, and that to do that, data needs to be in a place where it's accessible to everyone in some form of platform. So let me end there.